Welcome to the lecture series on numerical methods, a finite difference approach. In this lecture, we will discuss various finite difference approach methods based on like its convergence and stability analysis. Afterwards, several practical application oriented examples we will consider and solve that problems. At the beginning, first we will just consider like a different class of ordinary differential equations and the basic methods used in finite difference methods that we will just consider. And whenever we will just start this course like numerical methods in finite difference approach. So, why we are using this finite difference method, that first we will discuss here. Why and how it has been implemented in a system of equations or in the ordinary differential equation or in the set of partial differential equations, that we will just discuss here over. So, if we will just go for these numerical methods here, then first introduction section we will just consider that why we are just using these numerical methods or where it can be applicable or where we are just finding the difficulties that we can just use these numerical methods instead of analytical methods. So, then the overview of numerical methods, various class of numerical methods we will just consider, and then based on that methods we will just go for like different class of examples, and by choosing different space size or like increment of the space length we can just solve these problems. Then this numerical solution of ordinary differential equations based on like Picard's method and Taylor series method we will just consider. So, first thing I will just go for it like numerical method. Numerical method is an approach for solving various mathematical problems involving differential equations, curve fitting integrals, root findings through approximations rather than exact solutions. Especially if you will just see here like different class of problems, if you will just consider. Suppose if we are just considering like a curve suppose, and how we can just fit this curve with a best approximated polynomial suppose, or if you will just consider a differential equation suppose dy by dx, and if suppose it involves some of these complicated like boundary conditions. Maybe complications means we can just say that its domain is a very irregular shape, or we can just consider like if this boundary conditions maybe involve some nonlinear boundary conditions here. So, if you will just consider such type of problems, then how we can just treat that boundary conditions, or how we can just solve these differential equations in certain domains, that can be possible through this numerical method sense. Especially if we will have like nonlinear equations to find like roots, especially in the if you will just go for like basic numerical methods. So, several methods are used for the solution technique, like we are just saying that is as the transcendental equations, especially we are just using in that case like iterated method or like Newton-Raphson method or bisection method or regular Fulci method. So, different class of methods especially people are using to get the solution if this is system of equations or if the equation is a highly nonlinear in sense. So, especially to deal such type of mathematical problem by numerical method, an input is provided in the form of some numerical data, or it is generated, created, or is called for by the problem. Especially if we are just going for this numerical solution process, so we have to supply some data, and that data will be carried out inside the system through maybe by use of hand computation or by use of computers. We can just use this data inside the system through various arithmetic operations, satisfying the sum of the logical operations, and finally we can just obtain certain class of like outputs there as the results. And if these results are just satisfied with the physical phenomena of or the physical behavior of this equation or the problem, then we are just saying that this is the solution of the problem. So, to deal such type of problems, especially we are just using numerical methods. So, then the question arises that why numerical method? Due to this increasing complexities encountered in the development of modern technology, analytical solutions usually are not possible. Suppose especially if you will just consider a domain which is like So, this class of domain, especially this nonlinearity nature, if you will just see these corners, especially it is just existing, or if we are just considering this boundary condition, that is in the form of like u del u by del n plus like alpha u, this equals to suppose u square here. So, such type of equations, if you will just consider here, it is very difficult to find the solution in such cases. So, to deal such type of situations, especially we are just using some numerical approximation to first to linearize this nonlinear equations, then using some of this finite difference method or like finite volume method or finite element method, we can just obtain the solutions. Especially I am just considering here this finite difference approach, since it is easy to understand and it is like easy to handle and it is easy to understandable to the audiences. So, if you will just go for like a different class of problems, so then we can just visualize that how we can just move in a different form here. So, why we are just using this numerical method is that sometimes if we can just find these numerical solutions are obtained using high speed computer, especially when the geometry of the object is of like irregular shapes or boundary conditions are highly nonlinear in nature, that I have just explained, and we will just go to the next step, that how this ordinary differential equations represented here. So, especially if you will just see this ordinary differential equation, so this ordinary differential equation can be expressed either in the form of like x y dy by dx d square y by dx square. If it is like another order differential equation, so we can just write that as a function of x y dy by dx d square y by dx square dq y by dx cube up to d to the power n y by dx to the power n, this equals to 0. Especially whatever this equation, if it is just represented in either in a multiplied form or in a addition form or in a division form, especially we can just equate to 0 if you will just take all the right hand side terms to the left hand side. And if we can just express this differential equations with this dependent variable and independent variable, especially if we are just writing this function as in the form of like, if you will just see here, so that is like suppose x is there, y is there, dy by dx is there, d square y by dx square is there, dq y by dx cube is there, d to the power ny by dx to the power n is also there. So, here we can just say that x is the like independent variable and y is the dependent variable here, and especially this function f is the function of we can just say it is a function which is dependent on the independent variable x and dependent variable y and its derivatives. Especially we are just writing x y dy by dx, since sometimes we can just find that this differential equation can be expressed in the product form also, like we can just say that y dy by dx, or we can just say sometimes x dy by dx. So, that is why this f is called the function of independent variables x and dependent variable y with its derivative terms here. Then when we can just say that this is of order n or n minus 1 or it is of order 1, especially if the order of the highest derivative is n here, then we can say that this differential equation is of order n here, and its degree is equal to the power of the highest order derivative, provided neither y nor its derivative appear under radical sign here. Sometimes we can just find that these differential equations, especially it is written in the square sense, or it is in a like 1 by 3 power sense or 1 by 2 power sense, or some fractional powers or some of this like algebraic operations, it can be involved in this ordinary differential equations. So, first, to determine this degree of any ordinary differential equation, we should have to express in a free radical form, or we can just say that if the equations should be free of radical sign containing y and its derivatives. So, if we are just making free from the radicals, especially the highest order terms, degree will be the degree of this ordinary differential equation. So, that is why it is just written, it is its degree is equal to the power of a highest order derivative, provided neither y nor its derivative appear under radical sign here. especially if you just consider a differential equation that is in the form of like d square y by dx square here plus square root of dy by dx plus y, this equals to 0 suppose. First we have to make this differential equation to radical free. So, radical free means especially if we will just take the square of these terms, or we can just take square of this whole equation first, then we can just express it as d square y by dx square whole square plus 2y d square y by dx square minus dy by dx plus y square, this equals to 0 here. So, once it is radical free, we can just see that highest order term is here, that is d square y by dx square, and its degree we can just consider that as 2 is the degree of this differential equation here. So, once this order and degree it is known to us, then we can just go for this like initial value and boundary value, where we can just implement these values to get the solution of this equation. So, if we want to find the solution of this differential equations, especially if we will just integrate these differential equations, then we can just find some constants there. To find the values of these constants, especially we have to put either this initial condition or the boundary condition to get it free from these constants or independent solutions there. So, especially if you just consider this ordinary differential equation that is in the form of like nth order differential equation as d to the power n y by dx to the power n, as like f of x y dy by dx d square y by dx square dq y by dx cube up to suppose dn minus 1 y by dx to the power n minus 1. So, its general solution will contain n arbitrary constants which can be determined uniquely if n conditions will be provided. So, especially to find n conditions, especially if you just consider initial value problem, at a point if all these values has been given, like y is should have to be provided, y dash is to be provided, and like its nth order derivative term should be provided at a single point, we can just say that this is a initial value problem. Or in other sense, we can just say that initially if the value is provided to obtain the solution in a open form, then we can just say that it is a initial value problem. And if the conditions are provided like more than one point, that is called the boundary conditions here, especially 2 or more points if you will just consider. And the solution procedure, whatever the solutions we will just get, it should be satisfied with that points. So, that is why it is called especially the boundary conditions. So, I have just highlighted here, if you will just see that one. So, especially if I am just considering this one, like this section here, like if these conditions are prescribed at a single point, that is a solution is required in an open domain, then such problems are called initial value problems. And especially if these conditions are prescribed at 2 or more point here, the solution is required in a bounded domain, especially then such problems are called boundary value problems. A problem is said to be well posed if the number of prescribed conditions are exactly same as the order of the equation here. This means that if whenever we are just finding the solution of a nth order differential equation here, especially we can just find n arbitrary constants, or we can just say that it will involve whatever this methods you can just apply it over there. Like if you just use like a simple linear differential equations, you can just find that like second order differential equation, we can just find a like particular integral and a complementary function. This will involve like a second order differential equation means 2 constants it will be involved. To find like 2 constants there over, we need like 2 conditions there over to find the solutions, especially that is called well posed problem. That is, the number of conditions are exactly the same as the order of the equation. So, easily we can just find a independent solution there over. So, then if suppose a higher order differential equation is provided to us, then to obtain the solution we can sometimes reduce into a degree 1 equation also. So, like if this problem is defined in the form, if you will just see, So that is as like nth order term as d to the power n y by dx to the power n here, and all these dependent and independent variables, if it is written as like x is the independent variable here, y is the dependent variable, remaining derivative terms y dash, y double dash and y to the power n minus 1 here. And the initial condition are prescribed, suppose x equals to x naught, then at that point only first point y of x0 is defined and y dash of x0 is defined, y double dash of x0 is defined and y to the power n minus 1 x0 is defined here. So if we will just introduce like a variable, suppose z1 here, z1 in the form of like dy by dx here, and if you will just express z2 as in the form of d square y by dx square here, z3 in the form of dq y by dx cube here, and zn minus 1 as d to the power n minus y by dx to the power n minus 1 here, so that we can just write z1 equals to dy by dx. And especially if you will just take the first differentiation of z1 here, so dz1 by dx, especially this can be written as z2 here. And similarly z3 can be written as simple first order differentiation of z2 there itself. And likewise if you will just proceed here, we can just obtain d to the d of z n minus 1 d by dx, this as f of x, y, z1, z2 up to zn minus 1. Simply we can just say that with the prescribed initial condition at x equals to x naught, we can just evaluate all the values at the single point there itself only, since x0 is the initial value which has been provided for all the derivative terms involving the first dependent variable, that is all y there itself. Thus we can just say that a higher order initial value problem can be reduced to a set of first order equations here. Therefore, we can just solve these initial value problems only of a first order, that as in the form of like dy by dx, this is f of xy here, where x greater than x0 with y equals to y0 at x equals to x0 here. So if we will just go further like how we can just use any numerical method for such class of like initial value problems. So first method is we have considered here, that is as Picard's method here, that is especially called method of successive approximations. So in that case, if you will just consider an initial value problem that is in the form of like dy by dx, that as f of xy here, and x greater than 0 suppose, and y equals to y naught at x equals to x0, that is basically the initial condition it has been provided here. So especially if you will just consider this equation, and if you will just take the integration of this term here, that is like dy by dx, that is f of xy, where x is greater than x naught and y of x naught is given, that is y naught here. Especially we can just integrate this equation, that is in the form of dy by dx here, this as f of xy here. Especially we can just write as dy, this as f of xy dx here, and sometimes we can just write this one as like this is nothing but dy by dx as like dx here, and your range that is just defined as in the form of like y2 y naught here, and this is just defined x0 to x here. And if you just define this integration in a sense, that means that we are just integrating this range y to y0 whenever we are just finding this integration from x0 to x here only. So that's why we can just write this integration range as in the form of integration x0 to x here, dy as x0 to x f of xy dx here, which can be written in the form of like y of x minus y of x naught, this as integration x0 to x f of xy dx here. And if we will just define a particular relationship establishing in a successive manner, then we can just interpret this side value as the n plus 1th range here and this side value in the nth range here. And especially if you will just write in a modified sense this one in a complete form, especially we can just write this as y to the power n plus 1 x. This can be written as y naught plus x0 to x here f of x y to the power n x dx here, where n is varying from 0, 1, 2 up to like way. And especially we can just say that y to the power n denotes the nth iterated value here and n plus 1 denote the n plus 1th iterated value here. So, especially if we want to move in this method, we can just say that first we will just guess this value for y to the power n here, which can be used for the further calculation of y values afterwards thereover. So, if we will just go for a particular example based on like a differential equation, we can just write this one as in the form of like find the approximate solution by Picard's method for dy by dx equals to suppose x square minus y here, where the initial condition is provided as y0 equals to 1 here. Especially I am just signifying this one, this differential equation as a dy by dx, that is the first order differential equation we can just say, and this f of xy part it is just carrying like x square minus y part here, and the initial condition that is given as y naught, we can just write here y naught equals to 1 when x naught equals to 0 here. So, we have to compute this one, this approximate solution up to like accuracy of 10 to the power minus 3 here. So, for this calculation first we have to consider like x naught equals to 0 here and x range is given just varying from 0 to 0.2 here. And this formulation especially I have just discussed in the previous slide that we can just write this and the n plus 1th iterated step as y to the power n plus 1. This can be written as like y n plus 1 of x as y naught plus x naught to x f of like x y power n dx here. So, that is why if you will just see this problem here, then it can be written in the form of like f of xy means that is nothing but x square minus y power n, that is nothing but nth iterated value thereover, and dx is there and y0 is specified as 1 here. So, that is why this value is just replaced by 1 there itself. And if we can just take this initial estimate y0 equals to 1 and integrate this terms here over, then we can just write the first iterated value whenever n equals to 0 suppose. Then we can just write y1 of x, this equals to 1 plus x0 to x, this is x square minus y0 here, y0 means this is nothing but 1 for this one, and into dx this can be written, if you will just take this integration here, so it can be written as like x cube by 3 plus 1, this is like minus x here. So, if you will take this range, so that we can just write this one as 1 plus x to the power 3 by 3 minus x, this is x0 to x here, which can be written as 1 minus x plus x cube by 3, and all other the conditions like x0 equals to 0. So, that is why this x involving terms which takes only the 0 values since x0 equals to 0 here. So, next we will just go for like Picard's method of successive approximation for like second iterated term. So, if you will just consider the second iterated term here, so we can just write this is as y2 of x, and this is nothing but we can just write y naught term, and this is x0 to x, and the next approximation we can just say that is like x0 to x, and we can just write f of x y power of 1 here into dx here. So, y power of 1 we can just say that this is nothing but like we have just obtained 1 minus x plus x cube by 3 here. So that is why in place of like y to the power 1 here, I am just putting 1 minus x plus x cube by 3 here. And if integrating this whole term here, that can be represented as like 1 minus x plus x square by 2 plus x cube by 3 minus x to the power 4 by 12 here. And if we will just go for this error term here, so this means that whatever this improvement of the solution is just obtaining after next iterated step, if we will just take the difference of our 2 consecutive steps, we can just find the difference, that is nothing but the error in that step only. So if you just consider like y2 of x minus y1 of x here, so it can be written as like if you just see here last slide, the terms are like 1 minus x plus x cube by 3 here. And if you just subtract y2 of x minus y1 of x, we can just write this one as like 1 minus x plus x square by 2 plus x cube by 3 minus x to the power 4 by 12 minus 1 minus x plus x cube by 3 thereover. So this is nothing but x square by 2 minus x square x to the power 4 by 12 here over. So that it has been represented in the form of like here only x to the power 2 minus x to the power 4 by 12. So maximum error at x equals to 0.2 we can just obtain if you just put this value at x as 0.2 here and x as 0.2 here, then we can just find this value is greater than 10 to the power minus 3. But the question is asked that we have to find this error should be less than 10 to the power minus 3 thereover. So to find this accuracy of the error, we have to further move to the next step. So when this error will be justified, at that step only we can just terminate and we can just say that this is the final answer of this problem. If we will just go for this next iteration, we can just write y3 of x, that is nothing but like y0 plus x0 to x and f of x and y to the power 2 thereover and dx. So y to the power 2, that is nothing but this term we are just obtaining thereover, the whole term. And if you just integrate, the total term obtaining is in this form here 1 minus x plus x square by 2 plus x cube by 6 minus x to the power 4 by 12 plus x to the power 5 by 60 here. And again we will just go for the computation of like error. This means that immediate next step, if you will just consider like y3 of x minus y2 of x here. And if you will just take these differences, since earlier step we have just got here 1 minus x plus x square by 2 plus x cube by 3 minus x to the power 4 by 12 here. And if you will just subtract, then we can just obtain rest of the term, that is as minus x cube by 6 plus x to the power 5 by 60 here, and which is also greater than 10 to the power minus 3 here. Then we have to go for the further step, that is as y4x here. That is nothing but also y0 plus x0 to x f of x y to the power 3 into dx. So if you will just put that value again, then we can just obtain this y4x as 1 minus x plus x square by 2 plus x cube by 6 minus x to the power 4 by 24 plus x to the power 5 by 60 minus x to the power 6 by 360 here. And if you just go for this error computation at the same point, that is as x equals to 0.2, then we can just find that this error is less than 10 to the power minus 3. Hence we can just say that y4x is the desired solution within that given interval. So further, if you will just move for like a Taylor series method, since I have in the beginning of the lecture I have told that different type of finite difference methods we will first deal for ordinary differential equation, then we will just go for like higher order equations or partial differential equations. So in the Taylor series method, if you will just consider like a first order differential equation here, these equations can be written in the form of as we have discussed here, that is in the form of like dy by dx, that is nothing but f of xy, and initial condition y of x0, that is nothing but y0 here. So, if you will just consider this initial condition as y0 as certain value and x0 as certain value here, then we can just expand, like if you will just function is a continuous function in the neighborhood of the initial point, if you will just consider, then we can just expand the series in Taylor series form there. So, first we have to consider that if the function is defined at its initial point or at certain point, close to that point this function should be continuous. If the function is continuous at the neighborhood point, then we can just expand in Taylor series form. So, if you just take this Taylor series function of y of x at x equals to x naught, then we can just write y of x as y of x plus x naught minus x naught there, and then it can be expanded as y of x0 plus x minus x0 y dash of x0 plus x minus x0 whole square by factorial 2 y double dash of x0. So, likewise it will just be continued like x minus x0 whole to the power n divided by n factorial y to the power n of x0 here. Especially we are just denoting here y of x0 is nothing but y of naught here, that is nothing but y0 x minus x0 y0 dash plus x minus x0 whole square by factorial 2 y0 double dash plus up to x minus x0 whole power n by n factorial y0 n here. And especially if you just consider after the next immediate term of y to the power n term, especially this is called our remainder term here, and this remainder term especially it is just written r as in the form of x minus x0 whole power n plus 1 divided by n plus 1 factorial here. Then we can just write this as f to the power n plus 1 zeta, since y is expressed in the form of like a f of xy here, or dy by dx is represented in the form of xy, f of xy here. So, that is why we can just write this as f to the power n plus 1 zeta here, where zeta should be lies between x0 to xn. So, whenever we are interested to find the solutions for like y0 dash, y0 double dash and y0 triple dash etc., we can just proceed in the following manner here. That is nothing but like y of 0 is nothing but y of x0 here, and y0 dash, that is nothing but f of x0 y0 here, since y of x is written as f of xy here. And in the previous slide, if you will just see here, dy by dx I have just written as f of xy here, especially if we can just express y as a function of y0 dash, it can be written in the form of x0 and y0 here. So, based on this hypothesis we can just say that y0 dash equals to f of x0 and y0 here. And if you will just go for like a second order differentiation here, we can just write y double dash of x, that is nothing but d by dx of f of xy here. And if you will just go for this differentiation of this one, so then we can just write this one as like fx plus fy into, we can just write dy by dx here, that is nothing but fx plus fy f at x naught y naught, if we want to find the value y double dash of x naught here. So, then if you will just proceed like a third order differential equation, we can just write y triple dash of x, that is nothing but d by dx of fx plus fy into f here. Especially if you will just differentiate, then we can just obtain this one as fxx plus y dash whole square fyy plus 2y dash fxy plus y double dash fy, this one. And if it is asked to evaluate at suppose y triple dash at x naught, we can just say that we can just find fxx y dash whole square fyy plus 2y dash fxy plus y double dash fy at x naught y naught here. So, to find this values, first if you will just use these conditions, especially we can obtain the values at that points, also at the differential equations at that point also. So, for a particular example, if you will just consider like obtain the first 5 terms of a Taylor series expansion, then we can just write this Taylor series expansion first, that is like your terms like y of x equals to y0 plus x minus x naught, y dash of x0 plus x minus x0 whole square by factorial 2 y double dash of x0 plus up to 5th order term. If we will just write, then we can just apply there over that f of xy, as since this question it is just given that obtain the first 5 terms in the Taylor series as a solution of the equation dy by dx equals to half into x square plus y square here, where y0 equals to 1. Especially we can just write here x0 equals to 0, where y0 equals to 1 here. So, if you will just write this equation that f of xy equals to half into x square plus y square here, with x0 equals to 0 and y0 equals to 1, and for the first order differentiation fx, if you will just calculate here, fx is nothing but d by dx of f of xy, sorry, del f by del x f of xy, that is nothing but half into 2x here. So, that is why x is coming over here. Then if you will just consider del f by del y here, so half into 2y, so y is coming over here. Then fxx, one more differentiation, if you will just take for x here, then we can just get it as 1 here. Then if you will just take fxy, so if you will just differentiate this equation with respect to y here, then we will just get 0 term. Then one more differentiation with respect to y, if you will just consider for this term here, then we can just get fyy as 1 here. Now, if you will just put these values at y0 dash is nothing but f of x0 y0 here, we can just obtain this term as half here, and y0 double dash, that we can just obtain as x plus y dash here, that is nothing but half here. Since y0 double dash, especially we are just expressing that as fx plus fy into f here. So, that is why fx is nothing but x here, fy is nothing but we can just say y here, and f means that is nothing but y dash here. And if you will just put all these values at x0 and y0, especially we can just obtain this value as half here. Similarly, for the third order differentiation, if you will just go, then we can just find that first term it has 1 plus y double dash plus y dash into y dash, that is nothing but 7 by 4 here, and y fourth at x0 y0 is nothing but 5 by 2 here. So, then if you will just put all these terms, then we can just obtain this Taylor series expansion as 1 plus x by 2 plus x square by 4 plus 7x cube by 24 plus 5x to the power 4 by 48 here. And the last term, immediate next term, we can just consider as the remaining term there or remainder term there over. So, that is why this remainder term, if you will just see here, that is nothing but order of x to the power 5 here, since the series expansion is going up to 4th order term here over there. And for x equals to 0.1 here, for x equals to 0.1 here, we can just find the error term for this one. Thank you for listening this lecture.